Hi, everyone. So I'm Tony. I'm a senior technical consultant at Wolfram Research Europe. And as Alessandro has said, today we'll be going through our data science is more than just statistic talk. And the idea is that we want to kind of move away from the idea that data science is just purely a statistical exercise where you kind of grab your data, count it, find various statistic flags about them or various statistic properties about them, and kind of leave it at that. We're going to make the point that that data science is basically any sort of computation with data, where anything from statistics to any sort of computation we would class as data science. And what do we actually mean by computation? Well, that can, like I said, mean anything. So statistics itself, or it can be some modeling on the data. We can visualize the data. We can do machine learning on it to gain inferences or classify the data. Image processing and signal processing. We can kind of run solutions on it. So there's a bunch of things that we could do with data aside from just the pure kind of statistics. So the way we're going to do this is there's going to be a bunch of mostly example based, right? So we're going to go through a bunch of different examples of different types of data science that you can do within Wolfram language, different functions you can use, and just different ways that you can kind of you can manipulate and gain inferences from your data. Cool. So with that being said, we'll get into our first lot of examples, and this is using computation to kind of just find things to count. So that's the kind of most rudimentary part of your data, is counting it, knowing kind of what the data is and how much of it there is there. So there's a few different ways we're going to show, both for text-based stuff, text-based data, or also image-based data. So in this case, we'll use as an example the raw text for the Lord of the Flies book. So this is just one long string of the Lord of the Flies book. And what we can do here is create a helper function just to grab different string positions. So what we're going to do, I've got this plot name here. I can give it some name, right? I can give it some word. It will go in the text that we will define, and it will try and find the string position for that name. So if Lord of the Flies text has at the 10th position the string that we're asked for, the string position would give the number 10 back, right? String position will find multiple string positions, so we'll give out a list. So in this case, we are just grabbing the first out of those and then dividing it by string length, right? And just showing that as a smooth histogram. So finding the fraction in the text where this word occurs, and then plotting a histogram of those. So we're plotting I forgot to define the actual text. Let me do that first. So if I first define that, is it not finding the, I forgot to run my initialization. My bad. Let me just go to the last slide and do that. Just need to load the correct directories. Cool. Right. So if I now do this and load in my text properly, we can see that we'll get a smooth histogram out for each of the words that we gave, where it gives us an idea of the word frequency, of the word occurrence within the text, throughout the text. So we can see that, for example, the beast is kind of not mentioned throughout the start of the book, or not mentioned a lot. It's kind of foreshadowed in the starting chapters, and then is kind of the main, or we can kind of guess is the main talking point of the kind of apex of the book. We can also find the sentence with the most positive sentiment. So something you can do with text a lot is classify it. So you can say this has a positive sentiment, this has a negative sentiment, and that's usually done through machine learning. So you'll train some sort of model that can recognize, that can take in strings and extract features from that to it will help it kind of put it onto a sentiment space, where that sentiment space has positive and negative, right? And oops, I run that twice by accident. So one thing we can do is, using the classify function, there is some pre-built classifiers in Mathematica that we can just make use of. One of which is this sentiment. So if I call classify sentiment and then some input, I can get the sentiment of some input, right? So what we're going to do here is we're going to separate out all the whole text into text sentences. Again, notice that all of this stuff is just built-in functions, making all this manipulation of the data really easy. So a lot of the flies text sentences to separate into a list of all the sentences. Then we run classify on every single sentence, and we select the maximum positive sentiment. So what this classifier is going to output is the probability that that sentence is positive, and we're going to pick the max of that. So we're going to pick the sentence that has the highest probability of being positive, essentially the most positive sentence of the book. So let's do that, and that'll take a quick second. Gives me time to look at some questions if there is any. So someone says statistics as a field of mathematics includes all kinds of regression models, classification models, clustering, etc. So not sure what you mean here by statistics. I wouldn't, when we talk about statistics or data science is more than statistics, I think something you'll notice throughout this, even if we're being kind of 100% honest about this, even this classify statement is in itself somewhat a statistical operation, right? So machine learning itself is based on statistics. So to an extent, yeah, you're right that it's a very vague it's a very vague definition to give, but what we mean in this talk is mostly just that data science is more than the kind of bog standard statistical analysis that you might do on some data, right? So it's more than just finding just pure. It's more than just pure modeling, or it's more than just machine learning, or it's more than just one of those things. We make the argument that data science is kind of the collection of computation on data. Right. So here we got our most positive sentence. We are going to have fun on this island. Something tells me that they probably don't. I haven't read the book, but I will assume by the mention of the beast that they did not have fun on the island. So something else we can do is we can show we can kind of overlay multiple plots. So we actually named our frequency plot here that we made. We named it word frequency plot. So we can now overlay a plot of the sentiment throughout the whole book as well. So what we're going to do is we're going to use the same classify sentiment classifier, and in this case we're going to run it on the whole text. We're going to again use text sentences to get a list of sentences, and classify kind of distributes itself into the list. So we'll get the sentiment of every single sentence. And then what we'll do, if it's positive, we'll replace that with 1. If it's negative, we'll replace that with -1. And anything that is neutral or something else, we'll replace it with 0. So we basically get a bunch of 1 zeros or -1s. The min filter and this kind of times, that's just to kind of smooth out the output, and also the scaling is just to kind of scale the output to make it a little bit more obvious on the plot. Right, so if we run this now, there we go. We get a plot where we have our word frequency analysis overlaid on our sentiment analysis as well. So this blue line would be the kind of the inferred sentiment of that point of the book, right? So we can see the sentiment starts quite high, it starts kind of on the rise, and then towards the middle of the book gets it gets much darker, and then devolves towards the end. Someone talks about Lord of the Flies not being a happy story. Yeah, I can imagine. Cool. So let's talk about images. So this was fair enough with working with a string. It is much the same with working with images. So Mathematica will just have a bunch of built-in methods that we can call, or built-in functions that we can call to do various things. So in this case, if I remember right, this is a bunch of nanoparticles embedded into a medium of some kind, and we can do counting. So, back in the day, you could get a bunch of undergrads to sit here and count these manually, or you can now just kind of use computer vision or some sort of algorithmic approach to do this. And in this case, we can do a bunch of stuff. So here we've got a tab view of all the different things that we do, but I've left it open just to show how simple the code is. So first we have just a sample like part of this image just to show a sample of this. So we've got a sample part and we just resize it to 400 by 400 to a size of 400 by 400. We then clean it by using binarize. So what does that mean? That picks some threshold intensity value, and then it takes all pixels below that threshold and makes them 0, and all above that threshold into 1. So it basically makes every pixel into either a 1 or a 0. So we binarize our image. All we have to do is just run binarize on it, and that will decide on I will use some heuristic to decide on a threshold. I could also give it a threshold if I wanted to do this manually. So I can give it a manual threshold there. In this case, I just binarize, and also I run something delete small components. So something binarization will pick up artifacts from kind of bright parts of the image or little kind of bits that might be above the threshold. Delete small components will go through, and if there's any kind of noise looking components, any really small kind of singled out ones, it will singled out zeros, it will delete them, or singled out ones. That was right. Right. So we've got a binarized image now. And now we want to work out our distance transform, our distances between pixels. And then again, we just do distance transform. Colon negate just simply flips the ones to zeros and vice versa. Distance transform, to get that image adjust, simply just shows us the image as a way to kind of render the image. And finally, to get our maxima, we can just use a built-in function called max detect. And that's it. And then we've got our maxima here. You'll see there's a bit of noise that got picked up at the top, and it's actually not noise. It's actually when we cut this out of the image, you can see there is the start of another kind of particle there. Anywho, so that's how we do it. So essentially, we can just scale this up to our whole picture. This is what this is doing. It's using the same stuff: binarize small components, colon negate, delete small components. It's literally just going through all of this stuff. But in this case, it's going through it on our actual image. So if I run this, here we go. Now we can put an X, a white X, on each one of our maxima that we identify. I can make this red to make it pop a little bit more. All right, so I can do more than that. It's not just an image of X's or of highlighted X's. I can also kind of, for example, use that data to plot the distribution of those nanoparticles in the medium with smooth histogram 3D. So I can give it data and get an idea for the distribution within that medium. Cool. So we can now move to some other examples of using computation to now inject context to kind of pick up on things that might not be as obvious by just kind of loading the data or that we might not know just outright. So the first example is going to be we're going to be using some shipwreck data that is I think should come with this notebook. So we're going to load that in like so. So here's the data set is just a data set with a bunch of different columns on shipwreck. So this is the ship, the date it was sunk, a description of kind of how it happened or what it was, and the coordinates of where it sank. Right. So one thing we can do is we can create we can do a bunch of different analysis on this to kind of pick up on different contexts. So we don't know anything yet. We just know that this is shipwrecks. So let's do a word cloud. So we'll take all the descriptions and join them together as a singular string. So this is the data set. So we can give functions directly to it. So we're going to take all the descriptions from Rex, join them into a single string, delete all stop words from that, and then just run word cloud on that single string. And all that's going to do is going to create a word cloud for us of every single word, excluding stop words, that occurs in those descriptions. And for anyone that's not familiar with word clouds are a way to visualize kind of word occurrence. So the bigger the word, the more it occurs in that text, and the smaller, the less it occurs. So we can see that U-boat is actually one of our most common words. So we can start picking up the context that a lot of these shipwrecks might actually be from World War II. Right, so let's continue on. There's a bunch of attacked here, aircraft, torpedoed, right? So our most common words are all to do with kind of war: torpedoed, sunk, U-boat. Right, let's continue on. Let's make that smaller. Right, another thing we can do is we can get a histogram of our date ranges. Let's see what kind of our distribution of dates are of all our sunk dates. So if we do that, we'll see that, yeah, there is a big kind of concentration of shipwrecks around the 1940s, which is what we'd expect by what we saw up here, right? So we're seeing that now most of this data actually represents World War II shipwrecks, and that is mostly because most shipwrecks come from World War II. We can also plot them. So we've got coordinates up here. So we can just pass that to GeoList plot if we want to get a simple plot of every single coordinate on a map. And here are all of those. And we can see again, I still seeing the pattern that they're all concentrated around the kind of Atlantic, where the trade route cut off would have been in World War II. That is where German U-boats would have been kind of shooting down, would have been closing down supply lines for the UK. Right. Let's do more. So let's do a smooth histogram now. So we'll do a similar thing, but in this case, we'll do a histogram to get an idea of the kind of frequency of the frequency distribution in the of shipwrecks. So we'll see. Yeah, again, they're all concentrated kind of to the west of Britain. Right. So now let's create a nice kind of 3D visualization of all our shipwrecks, just to get a kind of a final visualization of everything. So first, we're going to just generate some view box dimensions. We will get the elevation data. So there is in Mathematica, again, if we need any external data, either there's a built-in function that gets it or a resource data entry that gives us that data for the most part. So a lot of the time, everything we need is just here. So geo-elevation data has a bunch of geo-elevation data. So in this case, I will get my box and convert it over to a geo position. So each one of these is a geo position. So and I will get the geo-elevation data for that geo box, let's say. Right, so we can do that, and the reverse is just because of the way I think geo-elevation data gives longitude latitude instead of latitude longitude. So what's this? Oh, I'm missing a geo library, sadly. That's a shame. I think it's because of the early version I'm using. Let's try this. Okay, so I will skip this bit. Yeah, this should work fine on your end. This is just an early version of Mathematica, and we're playing around with installs. Libraries go missing sometimes. Let's see if I can. Okay, we'll just skip this. We'll just skip this one because of the because I do need to grab some geodata. I'll see if I can fix that at the end. But we'll move into the next examples, which actually cover the same thing. The idea was we're going to go through shipwrecks and show how that kind of extends out to everything else. So if I just finish what I was doing, all we would do is we would grab that data. So we would grab the kind of auxiliary data that we need in the form of the elevation data. And again, if we wanted to interpolate a list interpolation, when it comes to geo positions and getting ship points, we can create here a helper function, which bounds all our points to our view box that we defined up here. And finally, we just generate some depth and rec data and plot that. However, sadly, I need the geo-elevation data for that, which we don't have right now. Cool. So if we had any other data, so in Mathematica, a lot of the data will come in as a data set, which is what this is. So we've just got some tabular data, and we can kind of start analyzing it again. So this data will have a geolocation, a geocode. We can plot that onto a geoplot. We can plot a heat map of that distribution to pick up on trends. I think this is food hygiene. Yeah, so food hygiene around Oxford. So we can pick up on trends of how food hygiene varies throughout Oxford. And I think there is also a national, throughout the UK. So we can see kind of the bigger the city, the more kind of lower rated establishments seem to be. And that could be for any reason. That could be because there are just simply more establishments, or because there is a direct kind of correlation between low hygiene rating and being in a big city. We can also plot food hygiene by town size to kind of, so we've picked up on this, and finally we can kind of get an idea. And we can see that that trend does seem to be a trend that as population grows to an extent, the food hygiene will drop, but seems to plateau at kind of a kind of 4.58. It seems to plateau around there. Cool. Can do a similar thing with London accidents. I'll skip through it a little bit more. Again, we bring in our data, plot our local points, get local densities, and then get a kind of bin density as well, if that's useful. But the idea is all the same. So there is a quick question that I do want to answer. So your package shipwrecks has no begin package, end package, and you use rex get at package. So rex is equal to the output of the package. So that's a good point. So there's a slight difference. So when I do get, I don't have to get a package. I'm just getting a file. What you're referring to is this, and this is slightly outside of what we're doing, but I think it's useful to show. Package. So if I've got some file where I want to define some packlet, some custom packlet that will have my own functions. So, I want to define them in their own name, in their own namespace, so they're not kind of cluttering up global. Usually, you would create a text file and you would put in it begin package, begin all your functions, and then you would define it. So then, when this gets loaded with get, all of that code gets evaluated, and the result that is returned is basically, it doesn't return a result, but you just get the definition for all of those functions. All that get does is get a file and evaluate it and return the result. So if it has a begin package, end package, it will evaluate that, and in effect, it will take all the symbols defined within there. So I can actually evaluate this right here and show that actually we've defined X in other places. But if I question mark X, we can see that now X is part of some packlet, right? It's within a different namespace. So when we do that, when we put that in a text file and do get on it, all we're doing is evaluating this, right, and returning the result, which the result, as you see, is nothing. There's no result is returned from this. So if my file instead only had some list in it, if I had some list 1, 2, 3, 4, and then I did get on this, I would just get the list back, right? It would just evaluate this. The result of that is a list. So that's what I would get the result to be. So that's what's happening here with shipwrecks. Shipwrecks just contains some raw data, so the raw data set for this data. And then when I do get on it, it evaluates it and loads that in. Hope that makes sense. So get is you don't have to use get only with packages. Get can be used with any file. Although nowadays we usually tend to prefer doing this. So we can also do import shipwrecks, right? And this will still load the data just the same. But in this case, I can actually do a bit more where get can't decide what elements to import. With this way, I can actually say, okay, I only want to import the expression list from that, and in this case, it's just the data set. Right. Let's keep moving. Cool. So, changing the viewpoint. This is a slight quick example because you won't have the data on this. So this was a customer project that we had a while ago of helping the team that was trying to build a supersonic car, and they had some data that they wanted to analyze to kind of figure out why there was some extra load on one of the suspensions, right? So what we can do first is just show that, just visualize, have a look at the raw data. So that data again gets loaded in here. And you'll notice, back to what we were saying about get, this is a .mx format, so it's binary, so it's been exported in a different way. So we're not doing something equals that, we're actually importing in definitions directly. So just remember that get is can be used for a bunch of things, just like most Wolfram language functions. Anywho, so we import that data. It has the name SSC data and has various keys associated with it. So RPM1FM would be the RPM of the car. L1R is the suspension load on the right wheel, I think. Right. So here's our raw data. We've got our RPM variance, and also our suspension load throughout our run there. Right. So we can apply some calculus to this. So we can do a just literally work out the differences on the data. So if I give differences of data, it will just give me a new list or a new data set with the differences between each data entry. Right. So it's just an easy way to do differences. Min filter again to smooth everything out. And then again, we can run our RPM data through that. So if I click this, we can move through. So this would be our acceleration, I think. Let me show this. Yep. So that would be our acceleration. So we gain the differences between velocities, because you can model RPM to RPM is proportional to velocity, so you can model RPM to be velocity, and such. The differences between the velocity would be the acceleration. So then we can get an acceleration plot just by getting the differences of our RPM. And then finally, we can overlay on top of that our throttle. So throttle is again just a data entry from our data set. Finally, we can apply some signal processing to smooth some data and visualize further the load on the front wheel. So that's just the list plot we had from earlier. But something else we can do is actually do a continuous wavelet transform and a scaleogram similar to a spectrogram for this load on wheel to see what frequency the highest load is at. And finally, we can change dimensions to get this load to RPM graph. So this will give an idea to the team of how load on the front left wheel varies with, it was front left, not right. So how load on the front left wheel varies with RPM. So through the whole RPM run, going up the RPM ladder and down the RPM ladder, now we get a visualization of how that load varies. And we can see that there is some kind of peaks that the team will have to look at. And if I remember right, the problem was part of the problem that they were having is that part of the wheel was going supersonic before the car was, and so was introducing a bunch of extra load on the suspension. Cool. So now we can kind of do a kind of an added step of generating even more data or modeling data with computation. So we're not only using computation on our data, but we're also kind of generating or kind of extending our data with that. So what we're going to do here is sound frequency estimation. Again, we're going to use some built-in functions just to again do some data science on this sound, right? So the best thing we'll do is just have the sound, import in. It is the sound of a car. I think my volume should be on. This should play on online for you guys. If not, it's basically just the sound of a passing car with the Doppler shift applied. So Doppler shift is when a car comes closer to you, its wave frequency gets kind of bunched up and it increases, right? So you'll hear a high frequency as something is moving towards you, and then as it's moving away from you, the frequency will lower. So it's that classic kind of ambulance sound as it drives past, and the frequency goes from higher to lower, right? And one thing we can do is use a neural network in this case that uses a specific method called creep, or a specific algorithm called creep, which is convolutional representation of pitch estimation. So we can use that, and it's built into Mathematica, so we don't even have to kind of implement it ourselves to just go from pure sound to frequency estimation, right? Or rather, to go from to model what our frequency should be depending on some other parameters. So we're going to take our Doppler shift model, C being the speed of the wave in our medium. So in this case, speed of sound. V would be our velocity of whatever is making the sound. A bunch of time and velocity variables and so on. So we'll actually model to that equation in a second, and then we'll get some insights from it. But let's actually do this. So we'll start with our sound. We'll define this. Just visualize a spectrogram quickly, just to show that that is in here. If you want a quick spectrogram of a sound, you can just do spectrogram of that sound, and this will have a bunch of options for you to use. Pitch recognize, as we said. So creep, we don't have to implement this ourselves. There is a pitch recognize function, and by the way, if you select any function and press F1 on that function, it will take you to the documentation. If you've got the local documentation, it will open that. If you don't, it will just go to the web page version. So pitch recognize does exactly what it says on the tin, just recognizes the pitch of a sound that you give in, but you can also change the method. There's various methods that I can use. So there's a yin-based algorithm, there's our creep method, a speech, a kind of vocoder-based fundamental frequency estimation thing, or you can leave it automatic and let it decide for you. But in this case, we're going to use creep, give it our sound, pitch recognize, delete any missing values that it didn't manage to figure out, and then convert everything from a entity into a quantity magnitude. So from a quantity, to a quantity magnitude. So for example, pitch recognize will give things out in hertz. So it will give things out like this. So this thing, obviously, for anyone that's familiar with the Wolfram language, this is not just a string of 10 hertz. This is a quantity 10 hertz input form, right? So quantity 10 of unit hertz. And that is just so it knows to add different units of frequency together, different units of length, different units of time, and so on. Cool. So we're just converting that. Quantity magnitude just converts all of those into normal numbers, right? So then we get a time series, and again, a symbolic representation of a time series, where that is kind of abstracting complexity away from us, so we can just do our data science. So here's a time series. It varies from time 0 to 4.9. It has this many data points. It is regular, doesn't have metadata, and so on. We can just plot it. So if I define it here and plot it, we can just see our frequency data. So this is just our raw data. Oh. Yeah, this version of Mathematica is being funny, so I'm just going to leave that at this. Right, so we can plot our frequency data. That's just the raw data, and then we can actually model the equation we had up here. So we've got a Doppler shift equation, and we can just model that by creating a bunch of alpha functions. So first, our relative velocity, which is defined by this equation here. That is just cropped from that. And finally, the full Doppler shift equation. Right, so now let's go model it. We can run. Again, we can grab the speed of sound by using continuity magnitude, passing our relative velocity with all our different parameters, passing our frequency. And again, this stuff gets passed in as a symbol, right? So all of this stuff is done symbolically. I'm not passing in numbers here. And here, these are not defined as numbers. I'm passing in a V, a D, a T0, an F, passing these in as symbols. So then when I finally get the model, I'm getting a symbolic equation which corresponds to the Doppler shift equation that I've got up here, right? So we've got our model, and now we just want to fit our data to it, right? So we'll use nonlinear model fit. Again, another built-in function. We just give it raw data, the model that we want to model to, and our parameters, right? And again, if we want to see exactly the format that we want to input those parameters in, F1 on the function, and we can kind of look at a bunch of examples and also look at the different forms that it accepts. Yeah, so these are just free parameters, and if it has a value, it would start the search from that value. Cool. Right, so then we get another symbolic object called a fitted model, and we can just use this now. We can use this this fitted model will work like any model where if I give it a number, it will give me an output, or if I give it an input, it would give me an output. So then I can just plot this. I can plot our frequency data, make this a bit bigger. I can plot our frequency data in gray, and then I can fit our model, the best fit of our model on top of that data to see how well of a fit it is to our data. And aside from that, the fitted models don't just have kind of the raw data points in there. They've got a bunch of stuff like the best fit line. They will have a best fit. They will have the best fit parameters. So for the best fit, these are the parameters that it's using for F, T, V, and T0. Cool. Let's keep going and talk about why we're talking about this computation, or well, why data science most of the time ends up being what we said at the start, which is kind of picking out statistical counters and counting things. And for the main part is because most of the time when you're doing data science, you don't actually know much about the data, and that's what you're trying to do. You're trying to figure out how much of it there is there, what, if there is any patterns in that data, if if there is any kind of relationships or whatever that you can pick out. But most of the time you're going in blind. So that's why most of the time we just, we start out with the counting and the kind of statistical pointers to just get an idea, and then we go on to kind of proper computation. Cool. So and we're going to talk about the role of automation in all of this. And Mathematica is big on automation. And in this case, I mean a specific form of automation. I almost mean abstraction. So this is automating a bunch of more difficult or kind of more involved processes for you in a way where you can automatically generate a classifier function or a predictor function using machine learning. So usually you'd have to implement stuff like that manually, whereas there is an automated framework for machine learning within Mathematica to just make it easier to make use of it without getting bogged down by the kind of machine learning science of it. So let me show you what I mean. So we'll talk about classifier again. First of all, we'll just grab some example data. And if you want example data to play around with in Mathematica, example data is a great function. It will have, as the name suggests, a bunch of example data on the Titanic, on planets, on just random stuff that you can use to either practice or even just actually use. Like the data is real data. It's not dummy data, right? So here we're going to grab some Titanic data. And what this is, yep. So what this data is a bunch of entries on all the passengers of the Titanic and their survival. So were they male or female? What was their age? What was the class that they traveled in? And that is labeled as their survival, either survived or dead, right? So then this is what's called labeled data. So we've got a bunch of labeled data for Titanic survivors. And if we wanted to now build a classifier function, a machine learning classifier function, where we can give it a new passenger, an unknown passenger, and it can tell us what are the probabilities of survival versus death if they were on the Titanic, well, we can use this data to train, and we use that automatic machine learning framework now. So that comes in the form of classifying this in this case. And remember, before we had the classifier can be used with existing classifiers. If I give it a string as the first argument and say classifier name, right, whatever that is, right, we can use the pre-existing ones, or we can use a different form of it without that. And now we're actually creating our own. Right, so I'm giving it the label data. I'm just leaving everything blank. I'm not giving it any options, and that should go off if the machine learning stuff is working. If it's not, I'll just open a different version of Mathematica. So that should go off, and I should enable my dynamic content. Oh, there we go. So that'll go off. Train. That will choose the best This install is being difficult. It will choose the best method to train on, and we can also change that, right? So at the moment, it's completely default. I kind of mentioned that quite a few times, and the main reason for that is that you can get way more in depth with it, right? So if I know that specifically my data would benefit by using a specific method, I can say that. So if we go down to methods, there's a bunch of different methods. So decision trees or Markov chains or nearest neighbors, neural network, whatever. If I know for a fact that one method is better than another, then I can choose to use that. I can choose to directly tell Classify to use that. Same with the feature extractor, same with kind of if you prefer performance over quality, all of that stuff you can fine tune yourself. All right, so let's see if this worked. So if we try on a new passenger, so say a first class male that was aged 46, this is it says that they probably died, and we can actually grab what is the probability of died specifically, so we get a bit more information, and we can see that they're very likely dead, so about 80% to have died. Whereas let's see, a first class female that was in her 20s, female in her 20s, let's say, had a much higher probability of survival due to them kind of getting on the boat sooner, getting on the what are they called? We'll just call them boats. I forget the name now. Right. So we can do a plot of this survival, right? If I want to see how, for example, age varies male survival, I can do that. So I can pass this classifier to plot just like any other function that takes input, and then get a nice plot of how the survival, how the chances of survival change or decrease, basically, or the probability of death increases as your age increases as a first class male. Cool. So Classify doesn't just work with strings. It doesn't, as long as your output is one dimensional. That means if your output is a single string of some kind or a single number or something like that, if it's single dimensional output, then your input can be any dimensional, right? You can give images in, you can give vectors in, you could give whatever. So here we'll just show a small example of doing the same, but with day-night images. So now we've got a list of images go to some label, right? In this case, we do the exact same thing. Classify this list of label data. That'll go off and do that. And then finally, when that finishes, I'll be able to just use it. Cool. Here we go. Right. So that then goes off and classifies these as day or night. Just a few quick things about Classify. So two things. One, the form of the data that goes in has a bunch of different. It has a bunch of different forms that it accepts, and again, all of that is documented in here. So if we go down here, so you can see your training data can be in any of these forms. So it can be a list of rules, it can be a rule of lists where your in values and out values are two separate lists. You can have this where you've got a interesting, the nth element of the list as the output. This confusing method, you can do associations where the key is the thing you're classifying, data sets, and so on. And another thing is that you're not, I've been talking about this automation framework, this automate framework. You're not logged down to it. There is a full-on manual framework for building networks from scratch, layer by layer, right? So you actually have both. You're not restricted down to the abstraction or the kind of full low-level access to layers, right? You can do either or some combination thereof. Cool. Let me keep moving. Let me drink some water first. So another role automation plays in all this is helping us find groups and patterns or making inferences. So in the case of making groups and patterns, again, we can use a few machine learning methods to group our data and see if there are any patterns with any patterns between the data points, right? So we're going to do some image analysis on some dog pictures. So here we'll import some dogs. I really need to enable my dynamics again. 1 second. Evaluation. This one. There we go. Go back to full screen. So here's our data set that we're using. It's just a bunch of pictures of dogs. And if we wanted to generate a feature space plot to visualize their similarity, we could create a feature extractor and manually kind of pick out features and build that plot ourselves. Or we can just use feature space plot, and that will kind of pick out features from this dog's data set and create a feature space plot for us. So again, let's show that. And while that's doing its thing, I will show its documentation page. Just to show that just like classify before, there is a lot of options where you can actually fine tune its behavior, stuck with the default. Then that includes methods. So the methods that it uses to extract the features. All right. So here we go. We see there's 3 distinct groups that is separated in. So we've got beagle type dogs here. We've got hairy poodle like dogs here and chihuahua like dogs here, right? So it's picked out, that these dogs look different, that their features are different between each other. It's created this feature space of with a bunch of different dimensions that could depend on a bunch of different things. We don't know what the actual algorithm is doing, but it is kind of grouping together any pictures whose features are the same in this feature space. So if they're close together in this feature space, then that's what this plot is showing. The main thing to get is that these features aren't human features, right? When we talk about feature space, it's easy to make the analogy of it could be one dimension, could be nose length, the other dimension could be hairiness or whatever, but usually is way more obscure and meaningless than that. It will kind of be like the texture of a combination of pixels and things like that, which differ for some reason between these groups, right? Cool. So we can do there's a bunch of other automated stuff that we can use features with. So feature nearest is something where this will give us now, if we use it on our data set, it will give us now a nearest function, which is a function that we can now use on any other input to find us what the nearest entry in our data set is to our input. So if we show an example of that, we can run this nearest dog on our test dogs, right? So we'll run it a bunch on a new test dogs data set. So we can see I'm giving it some input, and it's going to try and go into my data set and pick out the image that feature-wise is most similar to the input that I gave it. It's actually doing pretty well, right? So this one's pretty spot on, right? These are similar. So it's just finding the ones that lay closest on that are closest distance-wise in the feature space, right? So you see it did pretty well. So chihuahuas match chihuahuas, beagles match beagles, and so on. Cool. So we can do the same with predictions. So instead of just grouping together, we can kind of make inferences and predictions. So that is the other side of the automation of the machine learning automated framework. So there's classify, and now there's predict. So classify is, as you'd imagine, building classifiers, and all the feature stuff that we showed works on labeled data. Predict works on labeled data as well. Right. So the slight difference is that predict takes an actual tabular data set. Right. So we've got a tabular data set here of a bunch of properties of wine. So fixed acidity, citric acid, sugars, chlorides, density, pH, so on. And then some people have gone through and tasted this wine and gave it a wine quality score. So that's our labels. This is our labeled data, where it goes from some properties of wine to wine quality. Right. So what we want to do here is build a wine quality predictor that I give it a new wine, and it tells me what it thinks its quality is going to be like. So we'll show how to do various parts of that now. Right. So one thing we can do is get a statistics summary from the function repository. So there's a couple of things here. So the function repository extends the kind of 8,000 functions that you have access to. So by default, when you load up Mathematica, there's about 8,000 functions built in, right? But on top of those, there are some user written or kind of written by us, by like technical consultants or by staff at different points. But it's mostly just a repository where anyone can submit a new function and get it published here. And then at any point within a notebook, you can do resource function, name of the function, and use it. And that goes for anyone using Mathematica. So there is a lot on here, right? There is a lot on Ready. There's different categories. So here in geometry, there's Miller indices plot, right? So someone wrote a function for doing Miller indices plots specifically because they used it a lot, or they thought it might be useful, or whatever else. So now if you wanted to do this, you would just do resource function, Miller indices plot, and make use of it. And as you'll see, all of these are documented same as every other Wolfram language function. And the same goes for data, actually. So the data itself also comes from a Wolfram repository called the data repository instead. And this one is basically the same idea as the function repository, but instead of function, it's data, right? So it's real world data that people will take, put in a Wolfram language format, and give you the ability to very easily just import it into your notebook by doing resource data, the name of the resource data. Right. So there's a couple of others. There's the function, there is data, and there is neural net repository as well, and prompt repository. So neural net is for pre-trained neural nets, and the prompt repository is for LLM prompts. Cool. So with that said, we're loading our resource data set. We're loading our resource function statistics summary. And what does this do? Well, I can actually go to its documentation and see it's just going to generate a statistics summary about a specific column that I ask it to. So in this case, we just want the wine quality column to get a statistics summary for it. And all we'll do, we'll just go off and do that. So it'll give us a count, the mean of wine quality, standard deviation, min, it's 25%, median, 75%, and so on, right? So instead of doing this stuff manually, I think this is John McLean's function. John wrote this function to just give you an easy, quick way to get these metrics from any data set. Right. So to now build a predictor, all I have to do, this is even easier than the classifier. I take my data set and do a rule with what the column that I want to be predicting. So in this case, I take my data set, my wine data set, and say I want to be predicting the wine quality, right? And the performance score is just an option to give a performance score of quality instead of performance. Cool. So again, let's go off and train that. So in this case, it's using, you'll see the best method switch around as its heuristics kind of help it decide what the best method for your data is. In this case, it used gradient boosted trees, and we can just test it. So let's define a new row. So a new row with just random fixed acidity, chlorides, whatever, all the rest of it, and all we have to do is just wine quality test. We pass it to that classifier, and this wine gets a pretty good score, it seems, of 6.7. Right. However, we can do more than just that. We don't just get kind of a wine quality and that's that. We can actually ask this predictor for a bunch of other stuff, a bunch of other metrics for that prediction. One of which is called Sharp values. Sharp values will actually show you how much that data point impacted the final prediction. So the bigger the Sharp value, the more of an impact that data point had on the final prediction. So for example, alcohol has a very high Sharp score value, a very high positive Sharp score value. So that means it positively affects the final prediction a lot. Right? Whereas something like residual sugar is a minor Sharp value, that means it negatively impacts the prediction and depending on its magnitude, how much it depends on its magnitude, how much it affects that, right? And if I remember right, they should all add up to, I forget, I think it's the total minus the mean or something. So sharp values, let me just get the correct definition. Anyway, it doesn't really matter. We can actually just use this to get a bunch of different plots similar to sharp values. All that give us an idea of how different data points affect our final prediction, right? So then that helps us if we want to remake this predictor or improve it or make a different one. It gives us an idea of kind of what values are most important, what we should focus on, and also kind of what people seem to value most in quality wine, which, unsurprisingly enough, as we will see now, it is alcohol. Alcohol is by far the biggest predictor for wine quality. I guess this specific group that rated these really really liked their alcohol, because by far the biggest impactor was alcohol, and the biggest negative contributor was volatile acidity, which makes sense. Volatile acidity can make a wine taste kind of gone off, right? And then chlorides, pH, and so on, and we can see that the impact gradually gets less and less until we're down to the final prediction, right? And all of these kind of show a similar thing, but in different ways. This will show it for every data point. So we have cumulative feature impacts. We've got feature value dependencies, feature impacts for the whole thing, and also value dependency plot again for either alcohol or total sulfur dioxide. So this would show how alcohol, how the prediction depends on alcohol, how the prediction depends on sulfur dioxide. So alcohol quite it positively affects the final prediction quite a lot, whereas sulfur dioxide negatively affects it slightly, right? And same with this. These are kind of a different visualization for impact on the final score. But the idea is, you don't have to extract features. I don't have to extract features manually with a different function to use these. I can just directly pass in, and I don't have to do predictor either. I can just pass in my data set. So pass in in this case, data set, test row, and that would give me my cumulative feature impact plot for that test, for that prediction, sorry. Feature value dependency plot. Again, wine quality. This is the how the alcohol affects this test. So we'll see that it is quite heavily dependent on alcohol. This is on the whole, on the data set as a whole. So what are the feature dependencies for the whole data set, and how does what are the value dependencies on specific different parts of the whole data set? So instead of a single line, we'll get a bunch of lines for all the entries. Cool. So now let's talk about, after you've done all this stuff, after you've done all your data science, all your kind of all your modeling, usually you did that for something. You either want to deploy it somewhere, you want to visualize it somewhere, you want to distribute it somewhere. So this is about automating that part as well. Again, like I said earlier, Mathematica is all about automation and abstraction. It wants to give you all these it wants to give you this wide tool set that is that does really complex things in really simple packages. For example, if I wanted to deploy an app, right? So what we have here is we've got a simple application that grabs, there is this API here that will show you all all bike thefts around the world. So you can so it'll give you a bunch of lists of cities and how many bike thefts happen and where they happened in that city, right? So what we can do, I'm not going to get into the actual thing too much, is just a value plot of different data points from the data set that comes in. So we grab the latitude, longitude, we grab the number of bikes, and so on. But all we do is choose a city. So let's do Athens. Give it a second to load the data. And then we'll go off, grab the data for Athens, and plot us a, there we go. There is a singular, there is a singular documented, I think let's try London instead, just to show it a bit better, or maybe Berlin. Cool. But anyway, so we've got this dynamic dashboard here that works in our own notebook. And if I wanted to distribute, if I wanted others to use this, what I could do is deploy that online. I could deploy this as a web app. Again, traditionally, that would involve a bunch of other tooling, a bunch of other stuff. However, we've got this automate. We've got this this automated kind of deploy framework. One of which is Cloud Deploy. Literally, all I do is Cloud Deploy the backup. So this whole thing I defined as a symbol. So this whole dynamic module is defined as backup. So Cloud Deploy, backup. I give it some options. In this case, permissions go to public, so anyone can access it. Cloud object URL type environment, just to know that it is a notebook. You don't have to have that in there. It just helps. It helps it know what it's doing. And it'll give you a link. So in this case, it'll use a random link because I didn't give it a name. I can give it a name as well if I want. So bike app, I'll put it in examples. /backup, and now that's actually just going to go to /example/backup on my Wolfram Cloud account. I can open that. I will open on a new browser. I just need to log in. Okay, the login is taking a little bit. There we go. And then this thing will just load on our on the cloud. So I can now do let's do London. There we go. So this is all, again, it will do the exact same thing as the desktop version, just in the cloud. So it'll take a minute to fetch the data and render that plot. So here we go. So now I can send this to anyone. I can just send this link out. No, whoever I send this to doesn't have to have Mathematica installed. Whereas if I send this notebook, they did, right? They'd have to have Mathematica installed to open this and run it. Whereas on the cloud, I can just put it up on the cloud, make it public, and send out this link, or I can share from here or publish from here, various other things. Cool. So that is for front end stuff, or kind of stuff that requires a GUI. But what about stuff that's just an API? If I just want to put up an API that returns something, that's even easier. And this is one of my favorite things about the Wolfram language that I use almost every day. So if I want to put up a RESTful API that returns JSON, right? I can use this API from any other language. If I can call it using curl, right? So it's just a normal API. I use this API function here, where these are my inputs. So there's one input called class, and that is a string. One input called age, that's a number. One input called sex, that is a string, right? And that's going to go to our Titanic survival classifier from earlier. And all we do is this thing can be a function. Well, this thing should be a function for one. So this thing that the API, the second argument of the API is a pure function that gets this applied to as an input. So basically what happens is I've got API, actually we'll show it here. API function X, Y, Z. We'll just do X, Y. I'll have some function here. Function that can use, where is it? This one, there. So plus hash Y. So hash is how you, it's called slot, and it's how you slot in arguments from a pure function, and the specifically named slot, the one with names. So this works if the input is an association, like so, which it is in API function. So this actually, if you are going to use this will help. So I will do this X, whatever X is. So in that case, 1, 2, 3, whatever, and Y goes to 10. Right. So these will grab the correctly named key from that association. And this is what's happening here, by the way. So You write this function. When the API finally gets evaluated, these get made into, the inputs get made into an association like this, and that gets just applied onto the end of that. And then you can use the slots as required. Anyway, with that being said, let's actually show the example. So that's the wrong place. Cool. So now we can evaluate this. I will again do the same thing and put it on my Wolfram Cloud. I can open the link and you'll see it will actually give me JSON back where it says success false because I didn't give it any input. And I can give it input now. So question mark. By the way, for anyone that's not familiar, in the URL, you can give the endpoint, you can give it a query or an input by doing question mark key. So class equals value. So class equals first. And then to separate them, I can use %. So class equals first, age equals 20, and sex equals male. Cool, and they died. Right, that was a anticlimactic, but yeah, that's the idea, that I can give this input, and not just from here. I can do it from Mathematica, right? So I can do URL execute this URL. Let me copy it. So URL execute the URL that we just put up, and then some queries, right? So I'm just going to copy these. First, age 20, sex female. And again, that will just make the same API request just from Mathematica. And this goes for JavaScript. You can use Axios in JavaScript or Fetch. You can use, you can do curl from just the command line. So this can be reached from anywhere if it's public. Cool. So I think with that being said, we're kind of coming to an end. I'll answer some questions. So all I wanted to show here is that, yeah, just, essentially machine learning and a lot of what we showed is still in some way statistical science. However, the idea of the talk was to just kind of move you away from kind of being locked into the same tooling every time. So it's easy to get locked in to, you run statistic summary on something, you get the count of values, you might do kind of you might model it to some model that is mostly a guess or whatever, or you do any sort of analysis. But a lot of the time, what I've noticed is that people get really, really good at using one part of that. So they'll get really, really good at modeling. They get really, really good at regression. They get really good at machine learning. And a lot of the time, because Mathematica's tool set is so big, you can almost forget that that's there. You can almost kind of, never come across it and just, forget that it's even there and forget that you can make use of it. So that's the idea, that don't think if it is a complex concept, there's probably some sort of abstraction or automation that makes it accessible to you within Mathematica, whether that's image processing, signal processing, machine learning, whatever. Like there's even, I think you can analyze MIDI, you can do all sorts of stuff. So our role as humans is just to ask those questions, right? To ask, what am I actually finding out? To make the inferences once once I get those visualizations, once I get those statistical summaries, right? It is then my role to kind of to interpret that and also pick up on what it means for the actual data. Cool. I will put this up on screen while I answer questions. That is for our next webinar on when's the 18th? I think that's next week. Yep. So next week is on networks and graphs, and you can join it by either clicking a link in the I think there will be a link in the chat, or you can also just scan the QR code here. Right. So, okay, first question. If you want to add multiple rows for this test data of wine, do you create a list for each feature? Yeah. So let's go back to that. So if I want to test on multiple things, there's two things actually that you can do. You can create a list of them. So as a quick example, we can just create a list of them like this and map through it. That's one way to do it. So like this, and then I can, instead of applying this, I do map test. Yep, test. Oh, is this not? This association. Wait. Oh, I didn't define it. My bad. So yeah, these will be the same score because they're the same. Let's change something. Let's make this 9. Does that even? Okay, whatever. Right. So you can do this, but I think a better way, if you want to test on multiple things, is it predictor measurements? I think it is. So let me show you that one. Yeah, so prediction measurements, you can actually give a full test set instead of just a singular test row, and that will go through and work out a bunch of different stuff for you. So it will include all this stuff. So your mean square, it will like your rejection rate, log of likelihood, bunch of stuff. You can ask it for single plots. You can grab the whole thing. So, for example, let's actually do this. So predictor measurements, wine quality test. Right, that's the right syntax, I think. Let's just test it. It is not the right syntax. What do you want? Test value should all be numeric. Oh, it doesn't like the. I think there is a way to do it. So usually you'll use. Wait, they are all numeric. Anyway, that should work like that. I think there's something in this data that I've put in wrong that I don't have time to figure out right now. But the idea is that, yeah, if you want to do multiple ones, I'd use predictor measurements. It's probably better than just using a singular. And also, just to show, I'm pretty sure this can this gets distributed by default. Yeah, so you can, if you've got a list of stuff, just give it the list, and then you'll get a list of whatever. There's a bunch of ways to do it. How do you call a function? How do you call a function in the resource repository? So what you would do is resource function like this, and you'll see I get this little new button now. And if I click that, it takes me to the Wolfram function repository. And if I continue typing, there is autocomplete on these. So something like command line parse, which is one of mine, that gets autocompleted in. I think there is also, if I hover, I can go, this will download the notebook for that, or I can go to the documentation link on that. And if you want to upload your own, all you do is go here, submit a new function. This will download a template notebook that you would just fill in with your function, your definitions, and then write your documentation. Cool. How about embedding the backup in a web page or any given website? Yep. So you can embed stuff. So two things about embedding. You can just directly embed a Wolfram notebook. And let me show you that. Notebook embed. So you can, yeah, just use a library called the notebook embedder, like this. Zoom in a bunch. Yeah. So you can embed any Wolfram cloud, any notebook on the Wolfram cloud, like we just showed, basically that that backup was just a notebook on the Wolfram cloud. Any of them you can embed into any any web page, right? So what I can do here, it works similarly to React. If anyone is used to React, where we create a div here with a specific ID that then gets replaced by JavaScript, right? So there's Wolfram Notebook embed the link to the notebook, document, get element by ID, notebook container. So it works similar to how React will have the root div that it replaces. Right, and I think there's also there's an older way to embed. I'll just show this. So yeah, there's the embedder, and there's also, you can use iframes. If you're more used to iframes, you can do embed code of a Wolfram Cloud URL as HTML, and you will get some embed code, which is just an iframe, where you can just copy that, paste it into, whatever page that you want, and you can use it like this. I would say the embedder is probably a better way to go. It's much newer, and I think probably a bit more powerful.